Okay. Uh, I'll show my screen. All right. Let me see this one here. Okay, I just changed the measurement units of parents from dollars to $1,000. Okay, so what do you expect? This is $4. Okay, the result of this is $4. How do you expect the coefficient change if the unit measurement is from dollars to $1,000? Just the opposite way, right? The first answer is using thousands to dollars. Now it's $2 back to $1,000. So how does this change? How does that change? Leticia. Yeah. 0.36 times 1,000. Okay? All right. So that's C. That's C. Okay? Open as an equation. Okay. Then this is the output. So how does that change? From 0.36, which is just 2 decimal places, right? Now it times 1,000. So it changed to negative 356.77 something. And the high school rank, the coefficient of high school rank will not change because it isn't the measurement unit doesn't change anything, right? Okay. All right. Okay. That's saying that this is the original one, and I have this output. Then this is the explanation of the original numbers. Okay, so I students' financial aid grants will fall by 0.36 dollars for every dollar increase in his parents' ability to pay, holding constant of high school rank. Okay, does the sign and size of the estimate coefficient meets our expectation or make sense? Yes. Then this is the explanation for this. The I students' financial aid grants will increase by $87.4 for each percentage point increase in high school rank, right? Hiding constants of parents' ability to pay. Then does this estimation seems reasonable? It is. Okay, and this is the one that I'm saying that if the units of measurement of parents has been $1,000 instead of dollars, so I changed from dollars to $1,000, right? So the estimate coefficient changed from 0.36 to 357. So, whatever I make red ink or any colors, okay, means the point, the key points you have to, really pay attention to. So the size of the coefficient depends on the units of measurement of the variable. And we cannot use coefficient size alone to make judgment about the importance of a variable. Look at this one. You are not able to use the numbers of coefficients to decide the importance of the variable, because the coefficient will change if the measurement units change. You see what I'm saying here? So the coefficient here is just explain the relationship of the x variable to the y variables. Doesn't make any judgment about the importance of the variable. If you want to know whether this variable is important, we need to do the hypothesis testing, which is in chapter 5. We haven't get to that yet. Okay? All right? So make sure you understand all these foundations, okay? All right? Then this is a part that I need to do some explanations too. Okay, there's some names, okay, about this regression model. Okay, we have some terms, 3 terms. One is called total sum squares and identify TSS. And explained sum of squares is called ESS. And residual sum of squares is called RSS. Okay, let me show some algebra. Okay, the easy algebra. Okay, do not worry about it. Okay. The definition of total sum of squares, TSS, okay, is using the yi minus, this one is y bar. Yi minus y bar square and sum it. We call it TSS. And this is called total sum of squares. And since it is y, so this is talking about y, the variation of the y variables. Okay? Understand what I'm saying here? This is the one I just want to explain it is on our textbook, page 65, 66, and a little bit of 67. And ESS is using y hat minus y bar. Okay? And this is called explained sum of square. Okay? And RSS, yi minus y hat, is the residual, right? It's the residual. So this is residual sum of square, RSS. And let me show you some work, okay? Look at the definition of the TSS is equal to yi minus y bar. Okay? What is this? I don't want to have this. Okay? All right. Look at the second equation. Does anybody see something different between the first one and second one? This one is just a little bit math. Okay, bear with me, okay? Didn't you see that I put minus y hat and plus 1 y hat, and I have the original yi here and y bar here. So since I plus y hat and minus y hat, I cancel out, right? So this is equal to this. You see what I'm saying here? Is that clear? Okay, now it turned out to be 4 parts, right? Now I put the first 2 as a 1 parenthesis. Did you see that? And second one as this 2 as the second parenthesis. Okay? And still equal sign. I just put these 2 together, the first 2 together, the second 2 together. Okay? Now, this one plus this one square. In high school math, we say A plus B squared. A plus B squared is equal to what? Everybody knows, right? A squared plus B squared plus 2 minus A times B. And this is what I did here. Nothing new. Put a square it. So this is the A square. This is the B square. And this is the 2 times A times B. Okay? Then I want to show the math. What do I say? The magic of the math. Or even the beauty of the math. Okay? If you plug all these numbers in, this one looks tedious, right? It's turned out to be 0. How wonderful. Isn't this the beauty of the math? Or the magic of the math? Well, so since this tedious one looks, really troublesome, it turned out to be 0, so we can neglect it. Therefore, just only 2 parts left. So what is the first parts? Can you know this one? Isn't this is the residual? Square it. So this parts turn out to be this one. Okay? Then this parts, using the y hat minus y bar. And actually this one is what we call residual sum of squares, is RSS. And this part is called explained sum of squares, called ESS. Okay? So this means what? This means the total variation of the y can be decomposed into 2 parts. One is called RSS. The other one is called ESS. And what's the purpose for OLS? The purpose of OLS is to minimize the RSS, isn't it? Right? So if we can calculate the TSS, also we know the TSS can be decomposed in these 2 parts. Therefore, and the OL is trying to minimize this one and maximize this one. Since we minimize this one, that means we maximize this one, because y, as long as we have the y, this TSS is just fixed. We can calculate the TSS, just a fixed number. And this fixed number can be decomposed as the RSS and ESS. And if we use OLS methods, we can reduce the RSS as small as possible. Therefore, make the ESS as bigger as possible. Okay? So this is the magic of the math, it's the beauty of the math. Okay? So after I explain this one, and later on, I'm going to use some ideas to evaluate how good of the model. Okay? All right. And So this is what for my left. Okay. What is it? Where is it? Okay, so this is what I replace all this. This is in our book's equation. Okay. And this one, this is just what I say from the equation 2.13, that the smaller the RSS is relative to TSS, the better the estimated regression line fits the data. And OLS is estimating technique that minimize RSS and therefore maximize ESS. Therefore, we're saying that OLS methods, okay, which is a best estimator for the regression analysis. This is the foundation of the regression analysis. This technique is the foundation of the regression analysis. Any questions so far? So now you all have very vivid, mind that TS is equal to ESS and RSS, although you see a lot of equations there. Okay? All right. Then this is about the second session. Okay? Let's go on to the third session. So in third session, I'm going to talk about how to evaluate the quality of a regression equation and also describing the overall fit of the estimated model. So in these two sessions, we are going to learn how can you tell a good equation from a bad one. Once it has been estimated, do we have any criteria? Then do the estimated equation fits the actual data? Okay. If we say bread and butter of regression analysis is the OLS estimation, then the heart and soul of the econometrics is figuring out how good the OLS estimates are. Okay. Okay, I like to mention all of you, including me too. Many beginning researchers have a tendency to accept regression estimates as they come out of the computer or as they published in the articles without thinking about the meaning or the validity of those estimates. And this is sort of a blind faith. So that's why we learn how to evaluate a good model. Okay. So in fact, many good econometricians spend quite a bit of time thinking about what to expect from an equation before they estimate that equation. So now remember this one. Thinking about what to expect from an equation before they really estimate the equation. Once the computer estimates have been produced, however, it's the time to evaluate the regression result. So after you do the estimation using computers, actually your work is to evaluate this regression result. So how do we evaluate? Okay, there's 8 points. There are 8 points. You have to know it. Okay, you have to ask yourself. Okay, the first one is the equation supported by sound theory. So actually, theory is very important part. That's the behind, that's the rationale for regression equation. Okay, so you have to ask yourself what theory you are based on. And does this equation support this sound theory? The second one is how well does the estimated regression fit the data? And we will explain this one later on in 2.4 session. Okay, we just bring up these 8 questions you need to ask yourself. Is the data set reasonably large and accurate? Again, you have to have the correct data or enough sample size to do the research. Okay, so it's important. Then is the OLS the best estimator to be used for this equation? Although you didn't know how to, we just learned the OLS. But later on, if you learn more other technique, okay, then you can ask these questions. And this is also, the question you have to bear in your mind, that whether OLS is the best estimator. Any other estimators? Is there have any other estimators? Okay. And the other question is, how well do the estimated coefficient corresponding to the expectations developed by the researchers before the data were collected? How well? Okay. And or are all obviously important variables included in the equation? So it means that those X variables and those important variables, are they all included in this model? Or you need to ask that, has the most theoretically logical functional form being used? Means the equation model, the functional form of the equation model, whether this functional form is correct. Okay, then we'll get to that. This is in chapter 7. Okay, and this one is in chapter 6. Okay, does the regression appear to be free of major econometric problems? This is, more difficult parts. So this will be those topic were covered in the next semester, another course. Okay, so this semester we'll get to chapter 7 only. Okay, and so we will answer some of the questions. All right, and so I would say that the goal of this text is to help you develop the ability to ask and appropriately answer these kinds of questions. Okay, so those 8 questions you should bear in your minds. If you are a beginners, okay. In fact, the number is in front of each question above roughly corresponds to the chapters in which we are going to address this issue raised by that questions. So we will answer, one by one, answer all the questions one by one. Okay, again, I think we need to have something to really mention. So we expect that a good estimated regression equation will explain the variation of the dependent variable in the sample fairly accurate. And if it does, the estimated model fits the data well. So the overall fit of an estimate model is useful for evaluating the quality of the regression. And we also can compare the models. Okay, if they have different data set or different combination of the independent variables. Okay, we will get to this one later on. Okay, all right. Up to now, okay, there's one thing I have to also point it out. We can never be sure that one estimated model represent the truth any more than another, because all this estimated model is from the sample. So no one can represent the truth any more than another. But evaluating the quality of fit of the equation is one important ingredient in the choice between different formulations of the regression model. So if we evaluate the quality of the fit of equation, we can decide which one is the one we want to formulate as the regression model. Okay? All right. So now let's come to this very important. So this, we already get to the 2.4 session. Okay, this is describing the overall fit of the estimated model. And I want to introduce one important definition, which is related, we just say the TSS, RSS, ESS. Okay, coefficient of determination, R squared. Okay, how do we calculate the coefficient of determination? And what do we have to do this one for? Okay, so we say that the simplest and commonly used measure of fit is what we call coefficient of determination. And how do we get this? We call it R squared. And R squared is using TSS, ESS over TSS. Well, remember, we just say that all the variation of the y can be expressed as the TSS, and it can be decomposed as the ESS and the RSS. Okay, so what is the R square? R square actually is using ESS divided by TSS. Okay, using ESS divided by TSS. So look at the equations. And if I use this one, can be turn out to be right. This one can be expressed as this one. So R squared is this parts. So this is also equal to 1 minus this parts. Okay. Okay. Then we say that what is RSS? Residual sum of squares, right? And all else is trying to minimize this one, right? Therefore, for the total one, TSS, if we can decompose to this two, and we try to minimize this one. Therefore, if we can get R squared is bigger, then it tells us this model is better, right? This is what we say coefficient of determination. So the ratio of the ESS to TSS is called R squared. So the higher the R squared is, the closer the estimated regression equation fits the sample data. And this is called goodness of fit measures. Yes. Yeah, good questions. Let's see. Okay, I'll answer that. Okay, let's finish this one, okay? R squared measures the percentage of variation of the y around its mean that is explained by the regression equation. And since OLS selects the coefficient estimates that minimize the RSS, so OLS provides the largest possible R square given a linear model. That's why we're using R square to measure the fit of the data, the sample data. Okay? Yes. Yes. Data and oh. Mm-hmm. 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 Mm-hmm.
But in that statistical
Mm.
DEB,
Mm.
data
Data developed model.
data development says that when the R square is really high,
Mm-hmm.
it means that you multiply.
Oh, okay, okay. You mean that? But if you have multicollinearity problems, not only the R square, but also some other criteria you also can measure. So R square is not the only measures we use to measure the data. Okay, this R square is it. We will get to that. Okay, R square is one of the criteria we can measure. There's some advantage and disadvantage. No one, no, no, no one is perfect. Okay, so I will show you advantage, also disadvantage of the R square too. So I will answer, your question now is R square is not the only one measurement. Okay, then I will answer Edwin's and questions later on soon. Okay, all right. Then, okay, and since R square is using this one, anybody tell me the range of R square? Yes, 0 to 1. Since I'm using this one divided by TSS, right? So the sum of these two can be 1. Therefore, the R square, the range is between 0 and 1. So if you have the R square numbers closer than 0, means the model is not good. Close to 1, maybe is good. Okay, I will say maybe. I'll say why later on. But logically, if we have the higher R square, means this number is more close to 1. So it's better. Generally, it's better. Okay? All right? And so let's see this one. So R square is between 0 and 1. So the value of R square closer to 1 shows an excellent overall fit. And higher R square does not, okay, look at this one. A higher R square does not necessarily imply the changes in X leads to a change in Y. Okay, the higher R square doesn't necessarily imply the change in X leads to change in Y, as there may be an underlying variable which is hidden, which changes leads to the change in both X and Y simultaneously. Especially this is happened in time series model, but we haven't get to that. This semester, we are talking about cross-sectional model, data, cross-sectional data. When we using the data, which is time series, we need to use time series model. Okay, there's many time series model, R square is very high, but those hidden variable we didn't see. Maybe the inflation, right, is behind the all X and Y variables. We didn't see in the model itself, but we have the very high R square. Okay. And, since we learned that the higher R square, the better, right? Okay. So you have to remember, be careful that if you have the R square very close to 1, this should be viewed with suspicion. Why? They very likely do not explain the movements of the dependent variable y in terms of the causal proposition advanced, even though they explain them empirically. Means that this means that we don't do the causality effect. Even R square is higher. Okay, yeah. Mm-hmm. Well, that is only correct for simple linear regression, because simple linear regression, when we say the correlation is between 2 variables. So if we have simple linear regressions, that's X and Y only, right? And this R square is really the square of correlation coefficient. Okay. And in theory, R square can be equal to 0 or 1, right? And such a fit implies no estimation is required. And this relationship is completely deterministic. And the slope and intercept can be calculated from the coordinates of any 2 points. So if you have the R square equal to 1, means what? All the points are in the line. All the points are in the line. So in that case, we don't have to do any estimation. You just use any 2 points, then you can get all these equations, and that's what we call mathematical equation. All right. And one thing I have to also, let me see. Okay. And I think this the diagrams, which you can see from this is R square, it's very high, right? Although it is high as 95%, 0.95, but those points still not on the line, okay? And here, I like to answer the questions, okay? There is no simple methods of determining how high R square must be for fit to be considered satisfactory. I think this is the question I like to answer to Edwin. Okay, there's no simple methods of determining how high R square must be for the fit to be considered satisfactory. And usually in time series data, we often get very high R square because that can be significant time trends on both sides of the equation. You see what I'm saying here? Because X and Y variables are both of them are affected by the inflations or time trend. Therefore, the R square is higher. And in cross-sectional data, what do we mean by cross-sectional data? All the data have different subjects, but at the same point of times. Okay, this is what we say in cross-sectional data. We often get low R square because observation differ in ways that are not easily quantified. So do you ask me that how high is the R, how high is high, how low is low? Okay, I would say that usually in business world, if you have the data, something like 50, 60%, 0.5, 0.6 R square, which is high enough. Okay, and those in that education or psychology, if you have something like 30 or 40%, it's very high. So that's really depends on the research in which area. Okay, and you know that I used to be teach in accounting department. All the papers we read from accounting department is very, very low. The R square is very, very low. But I think the most important things we learn in this class, especially in business, we wanted to know the relationship between X and Y. So R square is not that important, but R square can tell us whether this equation fits our samples. Okay, and the most important things is to explain the relationship between X and Y. So the main topic in this course is hypothesis testing instead of just looking at all these numbers. This number is one of the criteria we have to know. Okay, so we have more important things to learn, which is in from chapter 5. Okay, after chapter 5 is really, really, it's hard. It's the hard parts and important parts for regression analysis. Okay, all right. So R square, there's no numbers. We say it is big enough or small enough. All right. And let me say something. Okay. Okay. We just learned we just learned coefficient of determination. Actually, there's some disadvantage of R square. Therefore, we need to introduce another one, which is called adjusted coefficient of determination. And what is the disadvantage of R square? I think, didn't I say something about this one? Okay, let's see here. The major problem with R square is that adding another independent variable to a particular equation can never decrease R square. What does that mean? If I have the model like this one, for example, is this, okay? And if I add one more variable, which you call x3, even though this x variables, when we say we want to have x1, x2 here, means that these two variables can explain the variation of the y well. Therefore, I would include x1 and x2 as an independent variable, right? But nowadays, if I just randomly choose one of the variable called x3, it's nothing to do with the y. And I collect the data and I plug this x3 into this equation. This expression tells us that I can get, if I have all this data, so I have all this estimated equation, so I can have the R square for this one. I also can have the R square for this one too. And this expression saying that if I add one more which is nonsense variable, into the equation, and the R square doesn't decrease. They always increase, but increase a little bit, very, very small. So R square, the problem is R square never decrease as long as you include any kinds of variable into the equation. Therefore, they are considered another criteria, which call is adjusted R square. Means that we adjust something from the original R square. Okay, and this is what we have here. This is what we have here. Okay, how do you compare the difference between R square and adjusted R square? Now, adjusted R square is put the bar sign. In our textbook, they're using the bar sign above the R and square, and they call this one is adjusted R square. Okay, let me write down something here. Look at these parts. Then we say that R square is equal to this or equal to this, right? Now look at this parts. Adjusted R square is equal to 1 minus RSS TSS. But divided by RSS divided by n minus k minus 1. And this one, n minus 1. In statistics, this is what we call degrees of freedom. All the degrees of freedom related to the sample size. Okay? And this is the number of data, n. And this is k is the number of x variables. Okay? So in other words, if I turn this one, I'll write down like something like this one. Okay? This will be 1 equal RSS TSS. And this is all divide, this is, so I have to turn the upside down, and it turned out to be n minus 1, n minus k minus 1. Okay, and can you compare these two? Especially this one. What is this? I mean, what's the number of this one? This is n minus 1, right? This is n minus k minus 1. The k is number of variables, x variables. So for example, if I have k equal to 2, since I use k, I should have multiple regressions, right? So if k equal to 2, n minus 1 divided by n minus, if k equal to 2, minus 3. So what's the number of this one? This is greater than 1, right? This number always greater than 1, right? Because numerator and denominator, numerator always larger than denominator. So that is greater than 1. Okay? Well, let's stop here, okay? I know you are all fed up what I give you today. All the materials you're already fed up. Okay, let's just stop here. And we'll continue next week or the following week. But go back to review all this material, okay? This is up to section 2.4. And you can also review all the recordings, okay? Let's just stop here today.